Okay, so hello everybody. So can everyone hear me? Just say yes if you can hear me. Okay, so thank you very much. So we will move on to the big second half of this course, which is about first order logic. Okay, and then let me start with some motivations behind the first order logic. So when you study propositional logic, it's closely related to what's happening in computer science, but it's quite limited. The language is only about reasoning true and false, and it's not really about reasoning about objects that exists maybe in the real world or maybe in some imaginary world. So more technically, what happens in the propositional logic is that the basic ingredients that we use to build the formula there are called atomic formula, and that atomic formulas do not have any internal structure at all. These atomic formulas are either true or false, a propositional variable P. So these are the basic ingredients from which we build a complicated formula in propositional logic. And they don't say anything about what some objects that exist in the real world are given in a given problem. So typically, when you solve some problem by encoding the problem into propositional logic, you choose this particular the propositional variable in a particular way so that it's a truth and false mean whether p is equal to 1 or p is equal to 0, express the type of property that you want. So in a sense, there is an implicit translation about what each propositional variable denotes. And that's not very ideal for when we want to use logic to express more, to describe a more complicated situation, especially if we want to formulate or formalize the real mathematics and mathematical statements, then propositional logic is not good enough. So, there is a huge, although the logic is not often taught in math departments, the logic has a huge influence in mathematics. So, in the mathematical proofs or statements, you'll often see many things that we are dealing with in propositional logic, and we will deal with in first order logic. But what we learned so far, all the things that we learned in propositional logic is not good enough to express the real mathematics. And this was one of the biggest motivations that people studied logic in the beginning of 20th century. Okay. So yesterday I told you about some of the very early work that introduced propositional, the first order logic. That's the work by Frege and another person that so the Frege introduced essentially what nowadays is called this classical second order logic with identity. But in terms of the innovation that he came up with is notion of quantification. So he's the one who introduced universal and existential quantification into the logic. And another person who did this is Peirce. I think he's a logician. He's a logician in the US. Okay, so before actually starting anything with the first order logics, let me give you, maybe you just go for this first and then tell you about the overall structure of what kind of thing we will do to define first order logic. So this is a typical statement of first order logic. It's not exactly Fermat's theorem, and there are some issues that I found later. So we have to have so instead of just this equality, we should have some other statements, say x is greater than equal to 1, and y is greater than equal to 1, and z is greater than equal to 1. So this statement, which is a statement in first order logic, expressed Fermat's last theorem. It says that for all n, here quantification ranges over all the integers, so all the non-negative integers. For all n, if n is greater than 2, then there is not a solution of this equation, which is x to the power of n plus y to the power of n and z to the power of n, where by solution we mean the integers x, y, z, such that these values should be greater than or equal to 1. So this is exactly the statement of the Fermat's theorem, and which we can express in the first order logic. So you can kind of see that why the theorem proving is not going to be very easy. I mean, especially if you ask for theorem proving for first order logic with respect to particular model that's coming from the number theory, answering this question by theorem prover is essentially amount to proving Fermat's last theorem. That's going to be not very obvious. I mean, not very easy. Okay, so in this statement, you can kind of get some feeling about what's involved in first order logic. First, in the first order logic statement, we have a quantification, and then quantifications intuitively, this universal quantification can be understood in some sense as an infinitary conjunctions, where the infinity can even range over uncountable infinity. But this is another way to understand this it's a universal quantification that you often use in the mathematical statement that also have an existential quantification. This again can be understood as infinitary disjunction, or you can understand it as just usual disjunction in mathematics. And then dealing with the universal and existential quantification, we need a lot of more machineries to define what they means exactly. And also, if you want to develop the theorem prover, we need some more device to deal with more kind of deeper insight about how to deal with these universal and existential quantification, because they often involve infinity. So anyhow, the one big change in first order logic is that it has a quantification. Second, the atomic formula that we used in predicate logic was either true, false, or propositional variable. Here, atomic formula has a structure. It's more complicated, and it's not just very basic case like a propositional variable P. Instead, it has something. It says something about some relationship between objects. So in this case, one atomic formula is n is greater than 2. This formula doesn't involve any logical connectives like quantifications or conjunction, disjunction, negation. It's just some very basic case where we state some properties about numbers. But this atomic formula has a more sophisticated structure. It uses less than relations, and it compares two objects. One is something called n, denoted by n. The other is the number 2, constant 2. And then the second atomic formula is more complicated. It uses equality, and then it involves several operations like this power, taking the power, additions, and so on. Okay, so atomic formula has a more sophisticated structure in first order logic. So these are the main changes. And then we're gonna see many we will formally define the syntax and semantics of first order logic. And this, in some sense, this syntax and semantics of first order logic is a device which allows us to include this sophisticated atomic formula, also which allows us to handle this universal and existential quantification. Because things are complex, we have to do a bit more work. So let me just show you some informal high-level picture first before actually defining first order logic. Okay. Right. So, I mean, this is more like pictorial descriptions about first order logic, and which hopefully give you some understanding about the big picture about what's really happening. In propositional logic, in some sense, if you think about what kind of things we are really dealing with, we are only dealing with the facts or properties. So these are roughly correspond to propositional logic formula. So what are the properties? Properties are like, I mean, the students A is tall, or maybe, I mean, so he is smart, or maybe he's, and so on. So these are the kind of some property that describe some facts, okay? So, and that's the situation in the propositional logic. But in first order logic, things are a bit different. We have, I mean, essentially there are two big participants. The one participant is some objects. So these objects are something for which we want to do some reasoning. These may be it can be numbers, or it can be in some cases it can be a graphs. Or maybe it's if a graph is a fictitious, it's some vertices in a graph and so on. Well, maybe sometimes if these objects are computer memories and so on. So these are the objects. So the objects, we don't really say it's a property. I mean, we can't really say the number 2 is true or false. I mean, this is something that we denote. That this is, I mean, something for which we want to talk about some fact. Okay, so there are one participant which is called objects. So one main actor is an object. Another main actor is like the propositional logic. So this is a propositional logic case, the first order logic. And then we have another thing which is called properties. These are some properties about the objects. Maybe say number 4 is big. Maybe true or maybe not true, depending on the meaning of big, but 4 is big. That's a one property. And graph G has more than 20 vertices. So this is another properties that we state, but you can kind of see the difference that objects are something which which are the main kind of actors or main participants in our description of property like a G and vertices and these numbers. But properties are describing some relationship or some facts about it involving one or more objects. Okay. So these are the two things that's really going on conceptually in first order logic. And then first order, the formalization of first order logic involves some devices that allows us to express objects formally, also allows us to express properties formally. So for first order logic, we look at the syntax. When you look at syntax of first order logic, we will see something called the terms. And we will also see something called formulas. And then terms will be syntactic objects, which denotes, syntactic things, which will denote objects. Formulas will be syntactic things, which will denote properties. Okay. And then we will also use the semantics. So our semantics will also have two layers. The first layer is going to be semantics of terms. So what does it allow us is if I have some syntactic objects, a syntactic entity that denotes term, then this is semantics say, okay, what kind of object is denoted by this syntactic entity. So that's what this semantics of terms will tell us. And also we will have so this is interpretations of terms. And then we will also have an interpretation of a formula. Okay, so just to sum up, the big change that you're gonna experience when you learn about first order logic is that now we have, in a sense, two layers. One is about terms, one is about objects. So we have a syntax for the object, semantics for the object, semantics for this is syntactic entities for the objects, and also we have properties, and then we have syntax, some syntactic entities denoting properties. And then we will have an interpretation of those syntactic entities. And then because when we define the syntax and semantics, we want to say, okay, what kind of expressions are allowed in terms and what kind of syntactic things are allowed as a formula. So we need so these syntax and semantics are parameterized in the first order logic. So it's not like first order logic, you can think of it as a programming language. where we have essentially two big types. One type is for term, the other type is for formulas. But this is a very strange programming language. It's a very extensible. So this entire language is parameterized. So plug in different parameter, you will have a different language. And the parameter for the syntax is called structure, no, signature, sigma. So I will explain what this signature is soon, but this signature determines the syntax of this first order logic language. And then to give a meaning for the first order logic language determined by the signature, we have to provide appropriate semantic things, which is called structure. So structure S for signature sigma. So this is gonna be a bit like providing the meaning for the base case, and then all the rest will be built inductively from this base case. Okay. So to sum up, there are objects and properties. There are appropriate syntactic device and semantic device to deal with both of these objects and properties in first order logic. Okay. So that's a big picture about what's happening, and then let's go back. So let's start to look at the definition of a signature. And as I said, the signature is about syntax. And as I said, in the first order logic, is a language that allows us to express objects as well as properties. And so there will be something called the terms, there will be something called formulas, but both of them are parameterized by this signature. Plug in different signature, you have a different language. So if you are interested in mathematics, for arithmetic, then there is one signature. And if you are more interested in graph theory, there is another signature. So, or maybe computer science applications, it will have yet another appropriate signature. And then the signature does is that the syntax of first order logic will be defined inductively, and signature determines the base case. In particular, in terms of formulas, in other words, syntactic entity for properties, there's a signature allows you to specify base case, which is called atomic formula. So here's one example signature. So this is a signature for number theory. And then in that signature, we have, the signature consists of, this bunch of tuples. So these are the syntax, okay? It doesn't mean anything. It says we have a symbol 0, symbol 1, symbol 2, symbol plus. Plus means actual plus. Who knows? It's just a symbol plus, symbol multiplication, symbol power, and so on. So we have a bunch of symbols. If the word symbol confuses you, then you can think of this as just we have a character 0, character 1, and then POW is a string, and so on. Okay. Now, for this signature, is a group. The component signature is a tuple, but it consists of 3 big parts. The first part is called the constant. Okay, so this signature contains a constant 0, 1, and 2. And then the signature contains so-called function symbols like a plus, multiplication, and POW. And then it also contains predicate symbols, sometimes called relational symbols. It's called, in this case, less than and equal. And these constants are base case, which we can use to construct some syntactic entity for objects. So in this case, a syntactic entity that will denote numbers. And the function symbol plus, multiplication, and power are the syntactic operations which you can use to build more complicated object. In this case, more complicated numbers. Okay, and less than and equal. These are the ones that will allow us to state some properties about the object as in the base case. Okay, so if you have the arithmetic expression built by 0, 1, 2, and plus multiplication and power, you can compare one is less than the other, express one is less than the other by using this less than relation. Also use the equality using equality relation. Okay. Okay, so there are 3 components there. More formally, signature is It's a collection of symbols, but it's grouped. It has three groups. The first is called first group consists of so-called constant symbols, and then this constant is just C and I'm gonna denote C and D. It also have a function symbols, and we will denote the F and G. The last group is called consists of predicate symbols that's denoted by PQR. And then function symbol, predicate symbols, we have what's called arity, which means that we specify how many arguments each function symbol will take. So for instance, the signature that you saw before, we had a plus function symbol, then our arity is 2. That's because it takes 2 arguments. And then POW, it also takes 2 because it also takes 2 arguments. Predicate symbols less than, we write 2 because it takes 2 arguments. But if I suppose we have a predicate symbol which say negative, so maybe is negative. This is more computer science like symbols. Is negative, that will take only one number. Actually, here the negative even doesn't exist. So let me erase this. Maybe a bit better example is even. So this is one predicate symbol we can add. This will take only one number, 1. So its arity is going to be 1. So signature, although we are not going to write these arities explicitly, if we specify signature completely, it will be 3 sets, a set of constant symbol, function symbol, predicate symbols, and over every function symbol and predicate symbol, we have this specification of the arity. Another way to think about this is a bit like a Java interface where we specify which kind of constant, the values are available, the constant expressions are available, and which kind of methods are available, and so on. Okay. So, and then in addition to all of this, to specify the syntax of a first order logic, we will assume that there are countably many variables, which will denote x1, x2, and so on. These variables will denote object, not properties. Okay, so in propositional logic, propositional variable denotes in properties. So it has a value 0 and 1. But in first order logic, variables denotes object. So in this case, it's gonna denote the numbers if we are talking about number theory. And here are some examples that I already showed you. This is a signature for number theory. 0, 1, 2 are constant symbols plus multiplication POW. They are function symbols of arity 2. Less than equal, they are predicate symbols of arity 2. So here I want you to do something. So here's one exercise. I will give you maybe 2 minutes to think about this exercise. So define a signature for propositional formulas. For propositional formula over propositional variable PQR. So this might confuse you a little bit. You think that propositional logic is, is about properties and what I'm talking about. But what I'm really talking about is that the choice of objects can be, a bit more like it can be more high level or meta. So I said in first order logic, we have objects and properties. And typically objects are like numbers. Properties are usually properties of numbers, but some non-conventional choices. Objects can be propositional logic formula. So then properties in this case will be properties of this propositional logic, okay? So the exercise is about define a signature so that we can do, these things. So we can denote, we have a signature which allows us to denote propositional logic formula as, objects. And then also we can reason about propositional logic using appropriate predicate symbol. So do this I will give you 2 minutes, try to solve this. Okay, so let me show you the answer. I think maybe using this is better. Okay, let me use this. Okay, so the signature for propositional logic is we will have. We said we have a propositional variable PQR only. So we have a constant PQR, and then also we will have a true and false. So these are the constants. So these true false are different from the logical true and false in first order logic that I'm gonna show you later. And this true false, I will underline this to mean true false in propositional logic. So these are the constants. And then we will have a conjunction operator, but I will also underline this so that this is not an conjunction in first order logic. This is an operator that we can apply to build more complicated propositional logic formulas. Disjunction operator, negation operator, and so that's it for propositional logic. And then we have so in this case, you say that we want to include the question wants us to include the logical entailment. So we will have a binary logical entailment notations. So this is a predicate symbol. Its arity is 2. The arity of this guy is 2. And this one is also 2. But arity of negation symbol is 1. Okay. So I'm going to show you the actual definition of propositional logic from first order logic formula next. But before that, let me, as a prelude, let me use this is a bit strange signature to express some properties about propositional logic with 3 variables. Okay, so this is we are using first order logic to reason about propositional logic with 3 variables. So one possibility is like, there are, I don't know how many of you heard about logic in the math department, and sometimes if you learn logic while you're using so-called Hilbert system, then you sometimes hear about so-called deduction theorem. So let me, well, in this case, just to make things convenient, let's use another symbol, which is implication. Okay. So then deduction theorem say in the, so this is from informal math notation. So deduction theorem say if you can prove some formula F implies G, and so if this is valid and if F is valid, maybe not deduction, I forgot the exact name, but if this is valid, this is valid. So then G is valid. So if F entails G is valid or maybe provable in some proof system, F is provable in some proof system, G is provable. So that's some theorem that is often stated. So and then so this type of statement can be written in this language, which say we have a for all x, y, z. Now in our logics, in our first order logic, variable x, y, z denotes propositional logic variable. Okay, so we have this predicate symbol, which and if left-hand side blank means true, and another some objects that we built by using x implies y. So we have and this is a roughly correspond to something like n is greater than 2. Okay, so we apply the basic predicate symbol to an object, to terms that's constructed with either base case or applying this arrow operations to x and y. If this is the case, and this is the case, this implies okay. So this is, I think to some of you this may be very confusing because we are having two kind of two kind of arrow implications. So we have this type of implication here. This is implications. It's not an implication in first order logic. It's an implication operator that we use to construct complicated formula in propositional logic. On the other hand, this is an implications of the first order logic. Okay, so we are constructing two objects, two terms. One is called true. The other is x arrow y. We construct two terms and construct atomic formula by applying this base predicate that entails. So then this is one atomic formula in first order logic. Same way, this is another atomic formula in first order logic. The last guy is yet another atomic formula in first order logic. And we are stating some relationship between these three, the relationship among these three atomic formulas using the logical connectives of a first order logic. So these are the logical connectives of first order logic. Okay, if I said what I said make you confused, just don't worry. I mean, it's just something very simple, but I think I'm telling you this because I want to make you more interesting than just reading the syntax. Okay. So then, as I said, if once we have a signature, then we have two syntactic entities. One syntactic entities for objects, and the other is a syntactic entities for properties. The syntactic entities for objects are called terms. Okay, sigma is a signature, so we have something called the sigma terms, and sigma terms are defined inductively. Okay, sometimes called by structural induction. And variable is a sigma terms, constant is a sigma term. And if we have a sigma term T1 and Tk, if we apply this function symbol in the signature, then that's going to be another sigma term. Then, so this is just something really obvious. So sigma signature is a bit like a interface, Java interface. And I mean, this is essentially say everything type correct, all the type correct terms will be terms. Okay, type correct entities will be terms. So variables, constants. For functions, we have to make sure that it takes, we say it's a function taking two arguments, we have to provide the two arguments. Okay, so that's just sigma terms. And So the one examples, if we follow these rules strictly, then the one sigma term in number theory looks like this. We have a constant 1, another constant 1, plus is multiplied there. So that corresponds to the third case. And then, so this is a one term, x variable is another term. So if we apply this multiplication operator, you'll get constructed yet another term. And typically, we are not writing in this prefix notations, we are writing infix notation because that's much more readable. So sigma terms are something that you expect. So it's a syntactic entity that we can build using informations from the signature. And it's defined inductively, either variable, constant, or function application. For formulas, so are the syntactic entity that describe properties. Formulas are also defined inductively, but its definition is what you expect. So we have two kinds of atomic formula, two type base case. One is for predicate symbol P in the signature. Okay, so this P is in the signature. If you apply this predicate P on the terms, the sigma term, the T1 of the TK, that's gonna be a formula. Okay, and right, and then this P should be in the signature, and then we have to make sure that the arity requirement is met in this case. True and false are formulas, and the others are a bit like what you learn in propositional logic. We have a negation and conjunction, disjunction and conjunction, and then we have a existential and universal quantification. Okay, so I mean, if you are, I'm sure that this, I feel like I'm saying something obvious in a very complicated way, but this is something most of you are already familiar with informally. It's just that we make everything formal so that we can reason about, we can do some proofs about all the state, all the syntax, all the formulas defined in first order logic. The first two cases are called atomic formulas. And so now here are two exercises I want you to solve. The first exercise is try to use this as a signature for number theory that I will show you what it is in another slide, and then express that there are infinitely many prime numbers using formulas, using terms and formulas that we just defined over and this signature of the number theory. And also using the signature of propositional logic we talk about, express it through Morgan's law. And then here's a reminder of two signatures. So this was the signature for the number theory. And maybe. Yeah, so this is the signature for propositional logic. Sorry about this. Okay, so use these two to solve the problem. So I will give you maybe 3 minutes to solve both of these. Okay, so let me answer both questions. Done. Okay, we've just here. So the for first question for the signature for the number theory, so that we can write it like so. Let's first think about the saying x is a prime number. So I think about how to express this in this signature. We said if x is a prime number, then x has to be greater than 1. And then whenever we decompose, we express x as a multiplication of two numbers, one of them has to be equal to 1. Okay. For y or z, if x is equal to y times z, so that implies y is equal to 1 or y is equal to x. So this is what prime number means, right? So then we can, so let's write a macro. So not equality. So write a macro and set prime. So you have to imagine that whenever I write prime x, it gets expanded to the right-hand side of this macro definition. So then to say there are infinitely many prime number, all I have to do is for every number x, I can always find y such that y is greater than x. Furthermore, y is a prime. So if you macro expand this prime y according to its definition of the macro, then that's the statement that express there are infinitely many prime numbers. Okay? And this universal quantification is the one which you use to express there are infinitely many prime numbers. And you see that we construct complicated object here, like y cross z. This is a bit more complicated object. And then there are various relational symbol we used. We used this x is greater than 1 and x is equal to y times z. So both of them are the atomic formulas where we use this given predicate symbols, equality and less. So it should be, yeah, so strictly speaking, let's just follow exact definitions. So then say, and this one is also. Okay, so that's how we did this. And then for the second question, which is about De Morgan's law. I mean, if I give you a reminder about De Morgan's law, it's really say if you have f and g, that is equivalent to negation f1, negation of g. And there are something similar for the disjunction. Okay, so let's express this the first De Morgan's law in using the signature that we talked about. So we say for every x and every y. So in this case, x and y will denote propositional logic formula. Okay? And then we have to say what you construct. The left-hand side is logically equivalent to what you construct on the right-hand side. So we use these entailed symbols to say, and then we construct bar. So the terms, and no, not on the bar here. So we construct in this term in the first order logic as a term. Okay, this propositional logic formula is now denoted by this term, and then the propositional logic formula here is now going to be denoted by another term. And then we say this left-hand side implies the right-hand side, and now we have to state the other direction, which is not x or not y. That entails x and y. So this is the expression of De Morgan's law using the signature for propositional logic that we talked about. Okay. So now let's move to the next. And then the one big picture about this syntactic definition is that the syntactic definition is inductive. So let me show. Let's go to this definition. Right. So this term and formula, both of them are defined inductively, which means that whenever you want to define something new on the syntactic formula, you can use inductive definition. Also, whenever we want to prove some properties about formulas, we can do inductions there. Sometimes this induction is called structural induction. That's because the induction goes over from the entire formula to the subformula over the structure of the formula. Okay. So one example is the definition of a quantifier depth. So this concept is not that important, but this one is mainly here to give an illustration about how you can use induction to define something over formulas. So quantifier depth is try to count what are the maximum nesting of the quantification in a given formula. So this quantifier depth for propositional logic formula, the base case, the atomic formula P, true and false, the quantification depth is equal to 0. And then the quantification of depth for negation is same as quantification depth over F. So here you can see that we are using structural inductions to define this. So, or you can, if you view this QD as an implementation in maybe Java or maybe Python, we are making a recursive call. So this is what we mean by using induction. And then this quantifier depth for AND and OR is just make a recursive call on F and G and take their maximum. Exists for case, we just make a recursive call and add by 1. That's because we have one extra quantifier here. So you can see that this definition is kind of the recursive or inductive definition that you will do if I ask you to solve this problem, for instance, in an exam. Okay, so this is the inductive definition, and then what I want you to do now is to define the two things using in this inductive definition. The first is a free X that has to return the set of all the free variables appearing in formula F. So we have formula F that can be X is greater than Y. So we may have something like X is greater than Y, and for Z, X is less than Z. So this is a formula which doesn't make sense at all. But we have a formula like this, then we say that variable X, Y, and X here, they are free variables. And we say this is Z is a bound variable. Free variables are the one which is not, in a sense, caught by the quantification. Okay, so these are the free variables. Bound variables are the variables used in the quantification. Yeah. So define this free and bound inductively, so that they can compute this set of free variable and set of bound variables. So I'll give you 2 minutes to do this. Okay, so let me show you how this works. So let's use the note. Okay, so let's solve the first, the define the free. So one thing that you have to do, go a bit beyond what's written in the slide, is that you have to do inductions to define set of free variable in a term, not just a formula. Okay, so we first, to solve first exercise, we're gonna define free of term t that will return all the free variables in t, and then we will, using this, we will define free of formula f. So it's a bit like if you you're defining two functions recursively. And the first function, free of t, there are three cases. We said the first case is free of constant c, then that's gonna return empty set. The second case is free of variable x, that will return singleton set x. And then the third case is that free of some function applied to t1 up to tn. So in that case, we just make a recursive call and then add all of these two things together. So combine them by the result of the recursive call by union. So it's going to be this one. So the definition is not very difficult. It's just something that you expect. Okay. So then now how to define free of formula f. So then we are just like before, we define the free for formula f using inductively. Then we have the base case is either true, false. In that case, there are no free variables, so we just return an empty set. And then the more complicated base case is some predicate symbol P applied to the terms T1 and Tn. In that case, we call the free operator defined on terms, okay? Or we use this definition of free variable on terms and then take their union, Tn. Okay? And then other cases are quite usually very simple. So if you have a free of some formula f, f disjunction g, or free of f conjunction g, then it's going to be just free of f union free of g, and free of negation of f, same as free of f. So far, really nothing really happens. I mean, the only place where something happens is this guy, the one base case. All the others are just making the recursive call and take their union. Okay? And now the big change is the next case to deal with quantification. So if you have a free of universal quantification, and actually it's behave the same as free of existential quantification. So here we call free on the part. This F, which sometimes you call matrix, we call free, and then we remove X. And then in that case, we remove X from there. Okay, so this is the definition of a free for, definition of free for the formula case. So you can see, as I said before, that another interesting case that happens is this quantification. So that's one, the definition of free. For definition of bound is also quite easy. So especially for bound, there are actually a multiple way of defining the notion of bound variables. But one particular definition we're going to adopt is that the bound variables are the ones which are quantified. We have an explicit quantification. So then really the base case in this case we don't even need to define the bound variable for terms, because I mean nothing is bound there, but bound for true, bound for false, and bound for propositional variables, predicate symbol Tn. So all going to be empty. And then the bounds for the other cases are just recursive coherent union. Okay, so I'll just show you one case. It's a bounds of F union bound of G. And now, so really nothing happens. I mean, if you just keep doing this using only these rules, I mean, my bound will be an empty set. But the only difference is if we have universal and existential quantification, in that case, we're going to compute bound of F, then we'll add X there. So this is the definition of bound variable. And there are some few cases which I didn't write here. But in both cases, so this actually the notion of free and bound variables are quite important. And then another point I'm making here is that free and bound variable can be defined by using inductions on the structure of a formula and terms. Okay. So and now there are some other concepts in versatile logic, something called the scope, and then and also another concept you have to clarify is a distinction between occurrence of a variable and a variable itself, and when an occurrence is bound and when an occurrence is free. Okay, so if you have that notion of a scope is quite something that's intuitive. So if you have an existential or universal quantification, like exists X or universal X, and inside the exists and universal quantifications, we may have some formula S that appears there, or maybe inside some predicate, we may have some term T appears there. Okay. So then both we say term T and the formula S are in the scope of this existential quantification. Okay, and it doesn't really matter whether it's a term or formula, also whether it doesn't really matter whether it's existential and universal quantification. So these kind of things, existential and universal quantifications, are called binders, and this the inside body of the binder is sometimes called scope of the binder. Okay. And then now we talk about an occurrence of a variable. Occurrence means that it's a particular instance of a variable appearing in my formula. For instance, if I have a formula, say X, yeah, the same thing, greater than Y, and exists X, exists Z, X smaller than Z. If I have something like this, then string S was some character S appeared twice or 3 times in this formula. And often when we talk about occurrence, we are focusing on not a bound one, but something like this guy and this guy. Okay, so we are talking about occurrence of a variable X. So the same variable X appeared 3 times here. And we have, typically we talk about first just appearance is called an occurrence. Third appearance is also called an occurrence. And then we distinguish occurrence of a variable as a free and bound by saying that if the occurrence is not in a scope of any binder, any exist or for binder, then we say it's a free. So this is a free occurrence. And this is a bound occurrence. That's because this X is inside the scope of this existential quantification. So now here's the one question. I give you maybe 30 seconds to think about this. Can an occurrence of X, so occurrence can be something like this guy, or this X is another occurrence. can one occurrence of X be both bound and free in a formula? The answer is yes or no. Just think about this and I'll give you an answer in 30 seconds. Okay, so the answer is no. That's because for each occurrence, it's either in a scope of some quantification like exists for all quantification of the same variable, or it's not in a scope. So if it's not in a scope, we say it's free. If it's in a scope, we say it's bound. So every occurrence, we can classify them as either bound or free. Never be both free and bound, okay? So that's an answer for the first question. Answer for so then now we switch the gear and now talk about variable, okay? So we say that a variable X in a formula is bound if the formula contains a quantifier over X. So this is a bit less related to what we are talking about on the top, but the second one is related. We say a variable X is free if it has a free occurrence in M. Okay, so in this examples, the variable X may appear multiple times in a formula F. And then we are asking, when you talk about variable X is free, we are only asking for just one occurrence that one or more occurrence that appears in formula F. So the last question that I asked, can a variable be both free and bound in a formula F? The answer is yes. And then concrete example is this example. So if you look at this example, variable X has a free occurrence as well as it has a bound occurrence. And then according to definition of this X is bound, X is bounded by this existential quantifications. So it's also X is both free variable and a bound variable here. And if a formula doesn't have any free variable, we say it's a closed formula or sentences. And some of the algorithms of first order logic we're going to talk about later. And these algorithms are working on only closed formulas. So just sum up. So we have quantifications. An important concept with the quantification is essentially where this quantification affects, so that the region of the influence by each quantifier. And that's specified by the scope. And then to say whether some variable is affected by quantifier or not, we introduce the notion of bound and free. And the formula without any free variable is called closed formula or sentences. Okay. Right. Okay, so this is the kind of description about the syntax of the first order logic. So then now we will move on to the syntax and the semantics of the first order logic. So as I said before, for syntactic part, I said the first order logic have two layers. One is for the objects and the other, so object, the other is for properties. And we said for first order logic, we describe how to specify the objects and properties using syntax. And the syntactic entities are terms and formulas. And they are all parameterized by signature. And then now we want to move on to the semantics. And the key part of the semantics is something called the structure, which is signature is a bit like a Java interface. And structure, you can view it as the implementation of a Java interface. It provides the meaning of declared operation in Java interface. So structure is a semantic entity. Okay, so here's a more formal definition of a structure. So given a signature sigma, with the sigma structure is essentially a semantics of that signature. So it consists of the 5 entities. the first entity is a non-empty set of universe. So this is the universe on which object lives. Okay, so if you want to talk about number theory, this universe is typically the set of natural numbers or a set of integers. Sometimes it can be the set of real numbers. Okay, so this is the kind of some setting where each object lives. And then for each constant symbol, so a symbol doesn't mean anything. We have to provide its meaning, specify its meaning as an element in this universe. For each k-ary, the function symbols, we have to provide its meaning as a function of the right arity. So it takes a k arguments and then returns a value. Beforehand, in the signature, it was just a symbol, doesn't mean anything. In the sig structure, it starts to mean a function there. Predicates, in the signature, it doesn't mean anything, just a symbol together with arity. But in the structure, it's going to be a relation. So P of A will be a subset of the the K products of U, which means that it's a relations on that takes about the K elements. So if something is inside inside this set P sub A, it means that the relation holds for this K tuple. Otherwise, that relation doesn't hold. So typically, in the usual the description of logic, when people talk about structure, they usually mean these first four elements. But in the lectures, I think that James wanted to make things simplify a little bit by adding this one extra component into the structure, which is in this course, we will also assume that structure provide the meaning for every variable. So we assume that there is a countably many variables in variables we consider. And then we are assuming that for every variable, we provide its meaning as a map element in this the universe of the structure. Okay? But if you look at later, maybe became interested in logic and look at model theory or some semantics of first order logic, typically the structure means the first four. So maybe in the remaining 5 minutes, we just look at a little bit about some concrete examples of the structure. So the one important distinction, well, some convention that we make in this course is that we are assuming the universe is non-empty. That has a huge influence because, I mean, if the universe can be potentially empty, then universal quantification doesn't behave as well as we want. So this is the assumption that we are adopting. But in some other logic books, they don't really adopt this assumption. They allow the universe to be empty. But anyhow, that's not assumption that we are adopting here. So here is one very typical example of the signature. So let me just show you signature of the number theory. Yeah. So here's so structure for very standard structure for the signature of number theory. So specific signature of the number theory that I wrote here, which contains 0, 1, 2, plus, and so on. And then the very natural structure is really interpreting everything in terms of non-negative integers. But the computer scientists, when they call natural numbers, they always start with 0. Mathematicians, when they talk about natural numbers, they often start with number 1. This is the computer science, so we are starting from number 0. Okay, so this is the underlying universe is a set of natural numbers starting from 0. So then 0 is interpreted as a number 0. Symbol 1 is interpreted as a symbol, that's number 1. 2 is number 2. Plus, plus, multiplication, multiplication, power, power, less than, equality, equality. Okay. So you might kind of feel that, okay, looks, nothing really happens because we are saying 0 is 0, 1 is 1, and so on. But there's a key difference. We are, in the signature, we are just have a bunch of symbols, okay, which doesn't mean anything. Here, we are assuming mathematical notion of 0, 1, and 2 that we are familiar with, and we are mapping symbol 0 into mathematical object 0, symbol plus sign into the mathematical plus operation, and so on. Okay. So this is a standard signature, but there are some non-standard one we can define. So here's the non-standard structure that we can define for over this signature of natural numbers. We say underlying universe is just a set with 3 elements: capital letter A, capital letter B, and number 5. Okay, so you just have a 3 element. And we map 0 to A, 1 to 5, 2 to B. And we said the plus is a binary operation on this underlying universe, but it's a constant function 5. Multiplication and power is a constant function A. Less than and equal, it's just something weird. It's A is less than B, B is less than B, and then that's it. Okay, so it's all very weird structure, but it's also legitimate structure. The above one is more natural, the below one is also legitimate, but the one above, the one below, both of them are legitimate structure over the signature of the natural number. So here's the one exercise I want you to do, and then, I mean, once you finish, you can just leave if you want, or you can ask questions to me. So the last question is, try to define a structure for the signature sigma p for the propositional logic. Okay, then that means you have to specify underlying universe, U of A, and then interpretation of a constant PQR, and so on, true, false, and operate, and so on. So that's what I want you to do, and then that's actually the end of the lecture. So yeah. So I'm gonna, so if you are done, you can leave. If you have any question, you can ask me any, regardless of what happens, I'll be here maybe until 10:20. So this sign, the R sign is about the, I mean, R sign is usually about the probability. This Ya sign, the second sign that you talk about, is about the validity, semantic implication. And you don't need to distinguish these two, because the probability, the proof system that we assume is complete. So these two things coincide. But in general, this sign, the first sign that Hyeong asked, it pointed out, is about probability. It's about what kind of thing we can derive using some systematic rules. The second sign is about what kind of things are true according to the semantics. So I just use R sign, but I could have used this Ya sign, the second sign.